you all hear me? Wonderful. Thank you very much, Kate, for hosting this session. It's a pleasure to be here, especially early this morning. I'm very surprised that all of you came out, but thank you very much. My name is Marta. I've been working with Michael Rose and Margarida from the University of Lisbon. Michael Rose works in University of California, Irvine, and I'm kind of the scientific daughter of these two, and I'm here to show you a little bit of my data from the long walk that was my PhD. So imagine this colonization scenario. A population after maybe a forest fire or a hurricane migrates to a new place, a new environment, or it encounters a politically novel nutrition environment with possible starvation. Their effective size may suffer some reduction due to founder effect or initial lack of adaptation. Some questions will arise. How will this population evolve in response to such a new environment? How will the reduced effective size affect the population evolutionary response? And what consequences will this have in the case of reverse colonization? I mean, when descendants of these individuals go back to the ancestral environment. So when everything goes right, natural selection is very good at producing rapid adaptive response in cases of intense selection, abundant genetic variation in large population sizes. A very cute and classic example of this in nature is the industrial melanism of distant Betullaria, where the white morph became a predation target when the tree trunks got darkened by the pollution. In the laboratory setting, there's a really neat experiment done by Michael Rose in the late 80s and early 90s in starvation-resistant selection, where two five-fold replicated stocks of Drosophila melanogaster were subjected to starvation-resistant selection for 20 generations in a population size of around 1,000 individuals. The results were very clear: increase in starvation resistance throughout time. Now, about reverse evolution. By definition, is the reacquisition by derived populations of the same character states as those of the ancestor population. This is contingent to several things, like the time they were exposed to the new environment, the value of fitness of the character involved, and so on. There was a very neat experiment done by Rose in the late 90s about reverse evolution during 50 generations, where five-fold replicated stocks of Drosophila melanogaster were subject to reverse evolution. On the left-hand side, you will find the reversion of development time in regimes with different evolutionary histories. And what we see, there was a reversion of all of them except this last one. On the right-hand side, it shows the percentage of differentiation from the controls in several life history traits. As you can see here in starvation resistance and fecundity. At low density, there was a reversion of all the characters to the ancestral state. So reverse evolution occurred with patterns that only differed according to the character study and evolutionary history of the populations. So everything goes well when we have the good conditions, but when we have small size, things change. So population size is a major factor affecting the evolutionary dynamics of fitness and its components. And its relation with several differentiation factors is different. Mutation accumulation, inbreeding depression, and loss of genetic diversity are stronger at smaller sizes, and genetic adaptation to captivity will be bigger and larger sizes. So the evolutionary performance and fate of a population will depend on the equilibrium established between genetic drift and natural selection. Being genetic drift stronger, smaller sizes, and natural selection effect stronger at larger sizes. So to test all this, I'm going to tell you a little bit of my experimental design for supported and reverse selection. 1975, Philip Truman and I went to Massachusetts and picked up some flies from the wild. Michael Rose kept them from 1976. I wasn't born yet. And those flies were kept in a 14-day regular culture of Drosophila until now. In 1980, I wasn't born either. 5 more lines, the baselines were formed, and these are the base of my study. In August 2010, I picked up those B lines and I derived 2 sets. One set of a population that I kept in small size and another one in large size. Half of them undergone selection for starvation resistance, the other half were the controls. And at the end of the day, I had the magic number of 84 populations to take care of. starvation resistant selection protocol was very simple. The flies were reared in vials for 2 weeks. The imagos emerged, they were fed high yeast diet to get their tummies full of fat, and then they were selected for starvation resistant by removing food, giving them either no food at all. When 80% of the population died, they were given the chance to recover, egg laying, and start all over again. For the small size populations, it was very, very similar, but the sizes were different. We started with 250 flies and then up to 50, compared to the 5,000 to 1,000. So the first thing we did was to see what happened 25 generations, during 25 generations of selection, what happened to the starvation resistant of the controls. They're supposed, not to respond, right, because they're not being selected. Well, that's wrong. We saw a significant increase in starvation resistance with time, but this was due not to the selection, but the selection for increased life cycle length that occurred while doing selection for starvation resistance. Nonetheless, no significant differences were found between size missions. In the selected lines, we got the results textbook. The large populations, well, all populations changed significantly throughout time, so natural selection occurred. And there were significant difference between the evolutionary rates of large and small populations, being the small populations with lower evolutionary rates. So these are just my show-off graphs of my 12 individual large populations and my 30 individual populations that show there's a lot of heterogeneity among replicates, especially in the small populations compared to the large. Then we went to check the indirect response to selection, and we used early fecundity to do that. In blue, we have the large stocks. In red, the small stocks, using the same large size control. There's no significant change throughout time, although there's a tendency to increase. And the small populations showed a significantly higher fecundity rate than the large ones, which is expected for the trade-off that exists between starvation resistant and fecundity. This difference, although disappeared when the effect of inbreeding was removed by using a small size control. So when we use a small size control to remove the effect of inbreeding, the difference between large and size populations disappeared. For the reverse selection experiments, because we didn't have enough populations already, we derived 60 new populations after 15 generations before selection and 20 generations in small size. These were subjected to 21 generations of reverse selection in a 14-day life cycle and regular food. So what happened was that the selected lines and the controls were different throughout the whole reversion process. And this did not change with time. So we were supposed to have, like we saw on the other reverse selection experiments, a reversion to the ancestral state, but some did, some went up, and some stayed the same. So as final remarks, we have that it's here demonstrated a higher replication than ever before in Drosophila, that the effective population size does limit the rate of response to both forward selection, directly as in starvation resistant, and indirectly as fecundity, and that the sustained effective size also limits the response to reverse selection. For me, the most important thing that this project brings is that the experimental designs that use small lab populations should be only confined to cases where the effects of low population size are of scientific interest, because they can confound the results. I would like to thank my scientific family, Larry Muller, Graves, Inez, and Larry for helping me out with this, my parents, and the 200 undergrad students that worked for me for over 120,000 hours to get this work done, and of course, my funding agents. Thank you. Any questions?
I missed why there's a reason to expect there might be a difference between forward and reverse selection.
I don't understand the difference in what?
So you reported results from both forward and reverse. Was there a reason to expect they might yield different results? Theoretically.
Well, there's reverse selection is usually not as strong of a selection, and involves a lot of things. Not only removal of the stress, like for instance starvation resistance, but the change in life cycle and all of it. There's a lot more to do with reverse selection.